Well, first of all, many thanks for the organizers for this amazing workshop. Really, so thank you for the kind invitation. I'm based at the Spanish National Research Council in Barcelona. And today I'm going to share part of my research focusing on phytoliths and other calcitic microfossils. The idea is to give an overview of main principles, information, taphonomy, methodologies, and also the applications with several case studies and main advances. So first of all, I will be focusing on the phytoliths and calcitic microfossils. I will refer to calcium oxalate crystals with ash pseudomorphs and to calcitic dung spherolites. So as I said, focusing in the formation and taphonomy, main methods, also sampling strategies in the field, and the main applications and advances, taking into account case studies, several case studies from the early farming context, high resolution, so with integration with other geoarchaeological techniques, and examples from ethnoarchaeology and experimental approaches. So the key research areas where I have been working in the last years are key regions on the origins and spreads of agricultural systems. We'll start with case studies in the Lebanon, in southern Jordan, also in the Upper Habur in Syria, and also with examples on ethnoarchaeological research. Of course, in central Anatolia, here site, Çatalhöyük, and also examples from the central Zagros, from Iraqi Kurdistan, with also some examples on ethnoarchaeological and experimental research. Regarding the materials, methods, and fields of research, it's on several fields of research, and it's not only, I'm not going to focus only in archaeobotany, also on integration with other geoarchaeological methods. Especially, I'm going to give some examples with integration with microcontextual thin section micromorphology, and some examples on ethnoarchaeological case studies and experimental research, and particularly I'm going to focus on the phytoliths and the dung spherolites and the water pseudomorphs. I give this example, this recent paper, it's focusing on animal dung, but with many examples. There is an interesting table showing the main methods and with indications of the advantages, the limitations of the methods, also how they integrate, and several case studies as well, but focusing principally on with the human with animal dung to investigations of human, animal, and plants investigations. The phytoliths, I don't know if you are familiar with phytolith. I'm talking about silica microscopic remains. The chemical, sorry about that. The chemical composition is opal, is silica, which is highly resistant to depositional and post-depositional processes. So they resist also high burning temperatures, and they can survive for millions of years. The formation of the phytoliths is related to the intake of the monosilicic acid, which is present in the soils, together with the water and other animals and aliments. Nutrition for the plant, and these are conducted through the aerial spars of the plant, filling up the spaces inside the cells, but also in between the cells. So the morphology can take the form of the cells, but also the intercellular spaces. For doing phytoliths, we have to do chemical extraction processes in the lab, very similar to those of the pollen. And the idea is to extract and to clean as much as possible the sediments to see these microremains in microscopic slides at magnifications between 400 and 200. Of course, it's critical, as many other botanical sciences, to build up modern reference collections, plants also from soils. This is the most complete one that you can find is open access. It's online available. The Phytolith core, it's a Phytolith reference collection. It comprises plants, phytoliths for modern plants from different parts of the plants, because the phytoliths are produced in the epidermal tissues of many plant species, and also from soils and fossil phytoliths from paleoanthropological layers, for example, from Old Dubai Gorge, having 2.5 million of years, and from several reference collections all over the world. This is an example from species taxons from the Mediterranean areas. And this is also from the reference collection of the University College London herbarium that Gordon Hillman built up in the 80s, and this house in the UCL, and comprises one of the most complete reference collections for cereals and for wild ancestors of cereals. And here I wanted to show these images because are, as you see, from main cereals, but also wild grasses. And the problem with phytolith is the redundancy. So similar morphologies appear in many different taxons and in different parts of the plants. Normally when we work with phytoliths, we can distinguish between big main groups. For example, monocots, inside the monocots, sedges, grasses, palms, then dicots from the epidermal tissues of the leaves or from wood, from bark. And we can reach taxonomical information into species level through morphometrics, phytolith morphometrics from the board of the International Phytolith Society. We've been working in over the last decade on promoting these morphometrical approaches towards the standardization of this approach, because it's critical for discipline to reach identifications into a species level. We published recently, a few years ago already, our recommendations for standardizing these methods. And also, in the bottom, that's another reference, which is more general, is on morphometrics in archaeobotany, which includes also the phytolith and also starches and pollen grains, and also macro remains, charred seeds and good charcoal. So if you are interested in the morphometrics, I recommend you have a look to those. As a practical example for what the useful of the phytolith analysis in these early agricultural sites, for example, this Wadi Rum in southern Jordan, which is now an hyper-arid region, as you can see. Several years ago, I had the chance to collaborate with Professor Donald Henry from the University of Tulsa. In this project, there was a part of paleoecological reconstruction through the sounding, reaching the levels of the habitat of the pre-pottery Neolithic of Nabu Nukela. And altogether, the paleoecological data demonstrate that the conditions were wetter than those of today, which is an hyper-arid site. Regarding the main questions here was to investigate the use of space in these structures, locus. And here was interesting to look the sampling protocol strategy was to investigate the distribution of the phytolith remains, because macro remains were completely absent, which is something which is common in these areas. And the sampling was done by squares, taking into account inside the installations outside these structures. And here the interesting thing was we found accumulation, especially in locus 2 and locus 3, concentrations of grasses, of cereals. Also there were concentrations of starches. Was Aline Emery Barbier from Nanterre who did the pollen and the starch study. And also accumulations of grinding stones. The grinding stones were in situ. We see here most of the grinding stones. And interesting was that we found the concentrations in the soils, and these concentrations were overlapping with the location of the grinding stones. And with phytoneomorphometrics, we were able to identify into a species level, measuring these characteristic elongate dendritics, which are produced in the inflorescence of grasses, particularly in the glumes. So there's a nice example of how to apply these microfossil studies. Also in integration, as I said, with the starches. The starches were also corroded, indicating so the processing in this grinding in situ grinding stones. And also here we look also to other calcitic microfossils indicative of dank. So indicating the dual use of these shelters, some as living and food processing areas, and others for keeping the animals as penning, establishing floors. So one of the approaches was the use of calcitic dank spherolites. These macro remains are calcium carbonate crystals, which are formed in the guts of many animals, that especially in herbivores and ruminants are the most producers, and are indicative of dank. They are found as a component of the dank. Are tiny, very small. They have about between 5 and 15 microns. As I said, serves an direct indicator of dank, but with the caution that these macro remains can be absent because of dissolution or because of calcination, calcination at high temperatures. We saw some examples later about experimental burning of the dank. Here you have some examples from the Barjabur reference collection from ruminants, especially. And for showing the application of these macro remains, here there's a case study in the Upper Habur in northeastern Syria. We worked together with a Japanese team from the University of Tokyo, led by Professor Yoshiro Nishiaki. Here you have the typical tell, so pre-Neolithic, with 2 houses in the same tell. There is also cemetery, so it's a place that has been always inhabited by the living and the dead. And here the Habur with water, which not always happens. 2 years later, the picture was taken in 2008, and 2 years later there was no watering. And here was great for doing some ethnoarchaeological research, especially focusing on the collection of reference material and focusing on the management, the use of animal dank. The sampling take account the fresh dank materials, also from pens, establishing floors, from building material, as dank is used also for plastering walls, floors, threshing floors, also can be introduced here in mud bricks, not deliverable, but was because the area, there is always animals, sheep, goats, cows all around, so it's possible that they get inside the building material. And also regarding the use of dank as fuel, it's a destroyed, not in use tanur type oven. And the idea was to build up reference collections for both micro remains, for phytoliths, and also for dank spherolites, and to build up a reference collection with herbivorous, fresh dank, and also omnivorous, because omnivorous animals, they also produce dank spherolites, but in lesser amounts. And the humans also, we do too. I don't have reference collection yet, but also we produce a few numbers of dung spherolites. Also, we have reference materials for soils, for penning areas, starting floors, building materials, etc. This reference collection is not only from Syria, from the Upper Habur, also we have materials from North Africa, from northeastern Tunisia, where the dung is used as fuel. As here we have an example. It's a tanur type oven that in this region is called tabuna ovens. It's orbital green dung, which is used for fueling. We did measurements of temperature within the burning fuel and also the walls of the oven. And we have also all this reference material regarding what is a fuel dominated by dung, or a mixing also with wood. This is particularly critical in many sites where the macro remains are not well preserved, or because especially in fire installations in herds, normally they are completely clean when we excavate. So here, with a very amount of ashes, we can distinguish and discriminate between, if the preservations are good, of course, the type of fuel that was used. In addition to phytoliths, we look also at other calcitic particles of plant origin, which are the wood ash pseudomorphs. Here you have some examples from this reference modern ashes from the laguna. And these ones are in fact calcium oxalates that are found in particularly in dicotyledonous leaves and wood and bark. And when these calcium oxalates are heated at around 450 degrees, these crystals become wood ash pseudomorphs, and they display these distinctive shapes like rhomboids, prismatic crystals, and which are very distinctive and also found very common in ashes. The sizes are between 10 and 50 microns. This is from the reference collection from the Tunisia area. I have Aleppo pine. We have a very small collection right now with several Mediterranean species. And as you can see, the crystals that it produces are completely different. That's oak, for example, these rhomboids, but in Aleppo pine are much more elongated. So the idea is they don't have a clear taxonomical value, but it's true that ashes produced by oak may be quite distinguishable to pine, for example. So that's another approach that can be used also to investigate fuel use. And in a site where macro remains, wood charcoal remains are scarce or even absent. As an example, let's go back to the same site, the Sekera Heimar in the Upper Habur, where we did the ethnographic work and the collection of the modern materials. Here, there's an architecture, buildings, rectangular buildings with plastered floors, gypsum, almost indestructible, these gypsum floors, and also very clean inside the houses, the buildings, which is completely different what happens outside in this common open species, dirty and plenty of combustion installations and ashes. Here, the pilot studies within the ashes in these oven pits were full of dung, so suggesting the calcitic dung spherolites, suggesting the use of dung as fuel, and also common reeds. The pragmatics, for example, was very, very common in these contexts. What happens inside the buildings, as I said, that's the micromorphology, the blocks, thin section micromorphology. This is the thin sections. was Lisa Meyer from Berkeley University, who did a micromorphological study. And they were very clean as well, inside the plasters, but also within the fillings, the preparation fillings of the floor. But with the phytoliths, we were able to see accumulations of plant remains, particularly grasses and cereals, inside the buildings, storage areas, food producing spaces. And this is an example of a gypsum line beam in one of these buildings. You can see us here also the plaster, the gypsum plaster, where the phytoliths were retained, even if it's swept and cleaned the buildings regularly. And it's an example which compares very well with this one, which is also a project by the same research team, the Japanese team in collaboration with the Azerbaijan Academy of Sciences, is also in the Southern Caucasus in Azerbaijan. Tepe is also a pre-pottery Neolithic site. And here they found also examples of clay beans, so storage within the buildings related to food processing areas, and cereal processing, that's the grinding kit, which was inside the clay bean, handstones in situ with these whitish remains, which are pure phytoliths. The phytoliths were directly mounted into the slides, very, very rich, completely disarticulated, not in anatomical connections. So it's completely disaggregated because of the grinding action. So what we have is the tools, the phytolith remains. Also, there was some seeds, mineralized seeds of Artemisia and some barley grains. And what was more interesting is the thin sections. Also was Lisa Meyer from Berkeley who did it. We found the phytoliths in anatomical connection and in parallel. So forming like a mat or what could be a small box for containing all this, the sampling kit. And this is critical to investigate the micro context. So to know where the phytoliths and the other remains are coming from, because without the micromorphology, it should be impossible to see that there was this woven matting here. So that's for illustrating the importance of the micro contextual information. This is what we've been doing in the last years also through the Marie Curie project that I developed in the University of Reading with Professor Wendy Matthews and with Roa Garcia Suarez. She will be presenting in a couple of days in the micromorphology session, and also joining our team tomorrow, starting a Marie Curie project with us in Barcelona. And in this area, we focus also in studying the indicators, Dank indicators, using also ethnographic materials and combining all these microfossils, the phytoliths, the Dank spherolites, the calcitic remains. Here we have examples from the ethnographic work made by Seon Anderson and Ertur Yaras in the late 90s in central Anatolia regarding the use of dank as fuel and the use of dank cakes. That's a dank cake is a cake which is used for fuel. It's still in use today. There are several techniques of manufacturing these dank cakes. One, the most simple, is to cut from a stabling floor, from animal pen, ruminants. Here, as an example of the thin section, we can see the trampling is the compactation of the soils with the dung, with the animals which are inside the pen. It makes this characteristic micro-lamination with the phytoliths and other remains. You can see here the dank spherolites, but also poorly digested plant tissues, sometimes fragments of seeds and other resistant parts, also amorphous organic matter, organic phosphate staining, which is orange or brown under the plain light, the microscope. And also, of course, large calcitic spherulites. In this case, is ubicaprin. Can see still the pellets well preserved. This tank cake was manufactured by molding in molds like the ones that are used for the matrix, but for manufacturing the tank cakes. And you can see still the phytoliths in anatomical connection and the parts which are fragile on macro remains preservation, particularly the epidermal tissues. So we can find the phytoliths from the leaves well articulated in situ. So with these materials, we can get a lot of information on the diet of animals, on the grazing and seasonality activities. In this case, this example was quite nice because we have all the information about the manufacturing of these tank cakes according to different seasons, and especially from in summer, springtime. There were also some that were manufactured in winter, and we can see that the composition is completely different. We have indicators of husks and efflorescence, floral parts of the wild grasses. And in winter, we have especially epidermal tissues and dicot material. All these examples are in also a recent paper that with Aroa Garcia Suarez and Wendy Matthews on a state of the art of this review paper on the approaches and the use of this reference material, but also the applications in archaeological applications in the sites in central Anatolia. We use this reference material for studying the Çatalhöyük stabling floors, the animal pens that were already identified by Wendy Matthews, the micromorphologist, since the beginning of the Stanford project. And in the deep sanding, the south area, there are already massive areas, these stabling floors, animal pens, compacted down. Here you have a view of the phytoliths in anatomical connection, these bulliform phytoliths from the leaves of grasses. And the same image with the cross-polarized light with the spaces of the phytoliths. And all these bright particles are tank spherulites. So what we have here is an animal pen, herbivorous or ruminant animal. What we find in the last field season of the Stanford project, very close in the south area of the site, very close to the deep sanding, another pen areas. This is an open space. You can see this line on orange, completely orange in the block itself, the detail, and in the thin section that was Aroa who made she manufactured the slides also, and she did the micromorphology. And we have a succession of compacted animal dung. And here, the diet was completely different. It was dicotyledonous leaves in anatomical connection with an excellent preservation. The interpretation was, there is here a clear manipulation of the fodder. Also, that could be related to animals that are more prone to browsing, like goats, for example. And also maybe it's related to seasonal activities, a diet that could be more related to winter than to other. It's true that the fodder can be also stored for the whole year. And here there's the reference to the chapter of the archive report. As you know, they're all in open access in internet. And here you will have the details of how the samples were collected, not only for phytoliths and microremains and micromorphology, also for biochemical analysis and other studies to investigate these open areas and the painting deposits. And what was interesting here is that in the field, we take the samples related to the blocks. Here, as control sample, we use a mud brick. This is a mud brick from a previous house, was already excavated. Then we have a sequence of a midden, like the ones that Karen showed this morning. It's beautiful middens with very organic, lots of charred pieces. And then all this is the sequence of animal penning. And in the lab, in the field laboratory, we already mount slides, non-permanent slides, and the composition was really clear, was the same. That's another profile, the same space. It's a huge open area. In the other profile, we have here a sequence on midden deposits with big charred remains and clays and mud brick pieces, and also pure phytoliths, sometimes these tiny whitish micro layers. And then the succession was exactly the same, the composition. When we did extractions in the lab later on, it was matching completely because of the preservation was excellent. And also we know that was an animal pen because of the concentration of Danke spherolites, lots of thousands of Danke spherolites. And last example, moving to the Zagros area, is in the framework of the CISA project led by the Matthews in the University of Reading. Another example, also building up in ethnographic modern reference material. Here also we have an architecture of rectangular buildings with floors, which in this space in particular, it's amazing the concentration of human burials. So it's the house of the dead. So imagine there is 78 at least burials with wrappings and matting floors. And a nice example here, also in this oven, which is related to this house of the dead, consisting of massive fuel remains. Fuel remains consisting on dung, because are ceruletic ashes with concentrations of Danke spherolites, and also phytoliths from rates, common rates, basically. And here was interesting to understand better what the taphonomy of these fuel remains, which are also found in other areas of the site, in middens, especially, and other combustion installations. So this research was also building in previous ethnographic work done by Robin Bendray and Sarah Elliott on the collection and the observation of animal management and the collection of modern dung reference material to get information on the diet, on grazing, browsing, and fodering activities, also about the grazing environment and the seasonality. And we also particularly focus on the use of dung as fuel, which now is residual in the modern village of Estansur. The gas was introduced in the 80s, and now is an activity that you can see also among these herders. They have sheep and goats, but they carry on together with the fuel from the village, which you can see is cow dung for heating, for boiling water, for example. And what we do is a program of experimental burning, but under laboratory conditions. We did the combustions in the laboratory to see the taphonomy, the impact of the fire, the heating, into the phytoliths, but also into the Danke spherolites. These are the results of the phytoliths. We did temperatures between 200 degrees and 900 degrees. As you can see, the heating effects, especially from 800 degrees onwards, but they still resist temperatures as high as 900 degrees. here we have this dendritic characteristic phytoliths at 900 degrees. But what happens is the melting. The phytoliths become to destroy. They make the bubbly, some bubbles, and dark completely, and they become amorphous. And this is an indicator of high temperature. So when we find ashes with melted phytoliths, we may estimate that they have suffered temperatures of 800 degrees or more. And the heating affects differently to the morphologies, different morphotypes of the phytoliths. We're not making detail because it's kind of too late. And the tank spherolites also, the heating affects differently. They are more sensitive to high temperatures. They completely, they disappear at temperatures around 700, 800. At 9, completely calcine, completely disappear. And here you have the compositions for the cattle, for the cows, and for the ovicaprines. It's a pattern which is very similar between the two different types of dung, but the differences are especially regarding the heating conditions in the oven. If oxidizing, the spherolites may disgregate earlier, calcine earlier than in reducing conditions. And also it's interesting to see what happens regarding the morphologies and the characteristics. They become darkened. Darkened was already observed in the darkening, especially in rock shelters and caves, in fumier deposits, the ones that are completely burned to sanitization for cleaning the caves, the spaces. In sediment sites, we can find also in the ashes, in oven, in combustion structures. And this happens, especially the darkening at temperatures about 550 degrees and 650 degrees. And the same, these features at 700 degrees, the possibilities of surviving become lower and completely calcine at 900 degrees. So it's interesting to study these micro remains, also to get some input into firing conditions in the sites. And that's it as a summary very quickly. Just I wanted to illustrate for the phytoliths and how other microfossils may serve the limitations that they have. But it's true that they offer a consistent data set for distinguishing certain plant species and also different park plants, which is also an interesting use for looking into a plant exploitation and plant use and also other farming activities. The importance also to have a look into micro-contextual high resolution studies to better understand the formations, the taphonomy, and the distributions in the sites. And also the importance of distinguishing the dung, because the plants in archaeophyte, they can come to the site from many ways, and animal dung, especially in early farming sites, that may be an important factor to take into account. Gives also critical information about animal management and diet and fodder and grazing and the use of dung as fuel and the importance of building up a modern reference and also experimental and ethnographic records. And that's it. I'm so sorry, I think it was a little late. And